All right, let's get the party started. So, welcome to the last part of this hackathon. So, I'm going to present now some more advanced DAOS API usage and more particularly focus on Python. And then we have a session, sorry, from Kaushik on how to use it with Darshan, and then some more Q&A session where we can do maybe some hands-on and answer any question you might have. So I'm going to present two middleware. I mean, you have seen before the full stack, right? There are many options, and I decided for this one to focus on two, and I'm happy to discuss more into the section at the end. First of all, PyDAOS is a Python module that is shipped as part of the DAOS packages. So you will see you can just load it very easily with just by running Python directly. And it's a new type of container. So we have seen so far mostly POSIX container, which is a namespace with files and directory. And in this case, we have a new type of container, which is non-POSIX. So basically, we build Python data structure directly on top of the DAOS key value store, right? And we decided to start with a Python dictionary. So we basically create this DAOS dictionary, dict, which is mimicking the Python dictionary interface, dict interface. Under the hood, it is using the DAOS key value store, and it supports all the traditional method of a regular Python dictionary. You will see later. But there is one key difference. Well, three key difference. First of all, they are persistent, right? If the program is stopped, we stop the Python runtime, you reload it, you recharge, you reload the DAOS dictionary, all the data you put in there is back, right? Unlike traditional Python dictionary, which are just in memory, right? The limitation you have with Python dictionary that they cannot go beyond the available DRAM. And in this case, since everything is remote, is stored in the storage, you can have a Python dictionary that are bigger than the amount of DRAM available on the node, right? And last but not least, they can be accessed in parallel from many compute nodes, and they support parallel insertion into the dictionary, including bulk insertion, right? We also added an extension to the Python dictionary interface to be able to insert in bulk many entries at once, right? It is obviously optimized over the network, and we pack multiple KV requests in there. There is documentation online. By the way, everything we presented with Mohamad is mostly in the DAOS documentation. So you can just go to docs.daos.io latest, and in the user here, you have all the documentation for DAOS POSIX container, Python, and everything. So it's a container. In the container, you can store multiple dictionary, right? And each dictionary is identified by a name, right? So you open the container and then you load one dictionary, and then you can do insert, remove, and so on. And you can have multiple dictionary like this inside the Python container, right? So I thought I will drive it more from the example, and this was run on Aurora on my pool, right? So first of all, you need to create a new container inside your pool. DAOS can't create. So this is the name of my pool. This is the name I selected myself for the new PyDAOS container, and the type. You might recall in previous slides that was dash type POSIX. And here, it's non-POSIX, so it's going to be dash type Python. So blah, 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 it created, it allocated a UID and container type Python. Then you load your favorite Python runtime, right? It can be the default one on the system or the one you have available through modules. And before that, you need to do module use / module file, blah, 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 that we had before, and also module load DAOS. And normally the Python module path is updated and you can just run import PyDAOS, right? And then it is available, it loads. And then to open the container, you just need to do dcont, pydaos.dcont, the name of the pool, and then the name of the container I've just created, right? And then I have an handle on the container called dcont. I can print dcont. I see that it is HP test my pool / my container, right? And then after that, it's open. I can create a Python dictionary or a ddict, right? An emulation of a Python dictionary. So in this case, I'm going to create a new DAOS dictionary, DD, by calling dcont.dict, right? I'm going to call the name I'm going to give to this dictionary stadium. And I can give an initial set of value, right? In this case, I'm going to put, so the name of the dictionary is stadium, and the key for every entry in the dictionary is the name of a city, and the value is the name of a soccer stadium, right? So in Barcelona, we have the Camp Nou. In London, we have Wembley, right? So I initialize it with those values. And after this call has been executed, I get back a DD object, which is stadium, and it's persistent, right? We have stored persistently in DAOS the content of this key value store. If I stop now, I quit the Python runtime, I redo the same stuff by import PyDAOS, dcont PyDAOS, blah, blah, blah. And then I try to print, I need to look up value. I will see them, right? So then a few examples when I have DD open, I'm going to add a new stadium, right? For Milano, I call it San Siro, and for Rio, Maracana, right? So I insert those value, and then when I print, look up the value associated in Milano, I get it, right? I look at the length. I have 4 entries, right? One for Milano, one for Rio, one for London, and one for Barcelona, right? I mentioned before, so again, at that point, if I stop the runtime, I reload, I reopen the container, I reload the dictionary, I print the content, I will still have it, right? I have this bulk put and bulk get extension that are not usually available in a traditional Python dictionary, where you can basically do multiple insertion at once, right? And it's going to be optimized over the network to minimize round trip, right? So Madrid, Santiago Bernabeu, and Manchester, Old Trafford, right? So I had this new value, then I look at the length, and I have 6 now. And then you can use all the traditional function you have on dictionary, like you can iterate over the key and the value and print the output. You can also test whether a specific specific key, is available inside the dictionary. And you can say, is Rio a city inside the dictionary? True, yes. Is Paris a city in there? No, I haven't added a stadium for Paris. There is also sometimes you might want to export the content into a real Python dictionary, right? And then in this case, you can do the dump operation. So you use the DAOS dictionary object, you dump it, and it generates a Python dictionary in memory that has the same content, right? Obviously, be careful. If you have added a lot of entry and doesn't fit in memory, you will run into trouble, right? But that can be convenient sometimes when you want to transfer the content of a dictionary in a DAOS dictionary or the other way around. And we also have implemented all the function to verify the content. So you can use, is this traditional Python dictionary equal to the DAOS dictionary? You can test it, and you're going to report true if the content is the same, right? And if one value is not the same, it's going to return false, as you would expect.
Can you show the part that you open existing dictionary?
Sorry?
Can you show the part how to open existing dictionary? Not how to create new one, but how to access existing one. Starting from the time when you connect.
Yeah, that's exactly the same. You do the same stuff here.
But
you do
that's
exactly
creates,
that.
right? That's second
That's create, and it also, if it exists, it opens it.
But I don't need to supply a second parameter with dict.
Obviously, yes. Here you don't need to provide that. You just do stadium, right?
Okay.
You
And
just do. Yeah, go ahead.
regarding exceptions, do I understand correctly that every time when we access this kind of virtual dictionary, it will do network round trip to get this information, return result, and in
Yes.
case fail, it will throw some exceptions?
Correct. Yeah.
Okay.
It always goes through the network.
Okay. And same story like with this redundancy and error checks can be associated with this container as well, all these parameters.
Sorry, can you repeat the questions?
The parameter control checksums, the redundancy can be
Oh,
associated.
yeah.
Yeah.
You can pass all those parameters above here, RDFAC and so on. They are the same. The only one you cannot change is the object class, right? The object class
Mhm.
by default, I think it's using replication.
Okay.
I don't think we have a way, but everything about checksums and so on is generic to DAOS and independent of the container type.
Can the parameters control the, I guess, what's called directory level or file level? I guess
So here there is no directory, right?
striping. Yeah, but
It's
dictionary looks like it's a kind of directory, right? Can it
yeah,
be
this is a flat directory basically. Yeah,
That's it. So there is no parameters for the dictionary that you can specify.
correct. Yeah, the dictionary are necessarily replicated. Yeah,
Okay.
we can actually add erasure coded value. I think we have never exposed it through the API, but I think this is something we can add actually, because DAOs at the lowest level support erasure coded value, right? Because we use it for POSIX.
Right.
Any other questions?
Is it safe to use that dictionaries for multi-processing? So is it protected on DAOS level, or someone has to do like wrapping to multi-processing primitive to do synchronization for concurrent access?
No, everything is if you try to insert the same value, you will get an error, and once it is executed, it's immediately visible. So it support concurrent update, and it's consistent. Yes.
Will it be able to control concurrency with maybe some timestamp associated when we insert the records? We want to insert only first one or maybe second one, depending on what value we specify the timestamp.
So you mean trying to do atomic insertion across a set of values? That's what you mean?
Let's say if I want to modify same value, but from different places, and I want to guarantee that the last insert wins, not the first one.
Yeah, that's the case.
That's
the
the case.
last wins, but you override basically, right? You override the whole value all the time. So the last insert, the last executed insert on the server side will win.
And this last comes from the fact that different nodes submit same request to update the same way, I guess, key.
Yep.
At different point in times, and they will be processed in what order?
Yeah, they will get a timestamp. So when they arrive on the server side, they get a timestamp associated to it, right? So the first one would get timestamp T1. The second one would get timestamp T2, right?
Right.
And at the end, after the execution, only T2 is visible.
Right. So my point is, can we supply this timestamp from the client side, not from the server side?
Yeah, I hear you. No, you can't.
Got it. Okay, thank you.
But DAOS has the ability to provide atomicity over multiple insertion, but we don't expose it through this API currently. So for instance, we could expose through this API transaction start, insert, or read, insert, transaction commit, right? And the whole transaction would be atomic, right? ACID transaction. But we have this in core DAOs, but we don't expose it through the SpyDAOS interface yet because we never came across a use case yet.
I talk about transactions for one specific dictionary or across multiple dictionaries.
It can be across multiple dictionary.
Okay.
So today the atomicity is at the single insertion. You are guaranteed that if you do a single insertion, it's always going to be the last winner win, and it's going to be consistent. But with this transaction model, it could be multiple value inside the same dictionary, or even multiple value in different dictionary. right? If you want to move one value from one dictionary to the other, we could do it in an atomic way if we ever wanted to do it this way, right?
Got it.
Any other questions? Okie doke. So a few more words here. Today we have only support dictionary, and there's been the work plan that has been planned for quite a few years now. We never got to it. Is to expand PyDAOs to also support NumPy array, right? Because as I explained before, we have key value store, but you also have arrays at the lowest level. And I think NumPy would be a good mapping for array. For DAOs array. And but we never got to it, and that's just some work that we would like to do at some point and expand PyDAOs with more data structure basically. And notion of tensors, right? That can be a good mapping for tensors to try to store them into a DAOs array. But this is not available yet. So you might see somewhere in the documentation that we have some plan to support arrays, but it's not done yet. So the next one is PyTorch
And
integration.
Johann,
Yes.
before you move on, this should have been obvious to everyone, but just in case, this is a custom format that's being stored in DAOS. So you cannot access any of this data through POSIX. There's no way to mount it through Fuse and be visible. You always use Python to go and inspect your data or read your data or access your data. So it's a
Correct,
bit more of an advanced usage that goes beyond what you would see on a parallel file system.
Right, but this interesting concept, it can be like distributed configuration store where you keep all these configuration parameters across applications, like for the whole cluster of a specific subset of applications. This is perfect model for this.
No arguments. I just wanted to make sure it was clear to any users that if you want to experiment with this, it's going to be different than maybe a usage you may have tried in the past.
Yep. Indeed. Thanks for clarifying, Kevin. So PyTorch integration. So I think it was at the end. So last summer there was collaboration between Enacta, which was a startup working on DAOs and Google Cloud to develop a custom data loader for PyTorch. So actually there are two modules, a data loader and a checkpoint module. The idea is, so today if you wanted to run, PyTorch over DAOs, you will configure diffuse and maybe use the interception library, right? But you will need to diffuse gives you very aggressive caching, right? But the interception library has no caching. So we were looking for a way where when we know that the data set is read-only, can we do more aggressive caching and a lot of optimization, right? So the idea was to write a shim layer that we integrate directly with PyTorch, which is called this PyDAOS.torch module that links directly with libdfs. So to be clear, it is using POSIX container, right? So you can mount through diffuse and copy your data or data mover, and then you can run PyTorch either through diffuse intersection library or use this PyTorch data loader. The advantage of the PyTorch data loader is that the libdfs is natively injected into PyTorch and does a lot of optimization for checkpointing and for data loading, right? So it links directly with libdfs, and it has a very high level of parallelism. So it can typically use multiple network context. I will present the two modules next, but there are some optimization coming that we haven't done yet. Today, we still have the limitation of one PyTorch instance can only use one network interface, right? And obviously, when you run PyTorch, you don't necessarily have you may have one per GPU, I don't know, or two per GPU, given you have two tiles, but not necessarily one per core, one process per core. So that can be interesting for us to support multiple NIC per PyTorch instance. That's something we are looking into. And also the other interesting aspect is that when using PyTorch, we can actually directly in the data loader or in the checkpoint module get a reference to the GPU buffer. So without using GPU direct storage from NVIDIA or anything that require to use CUDA and CU file, a specific abstraction. If we are integrated directly with PyTorch, at some point there is a way to get the buffer on the GPU, either for checkpointing or for data loading. And then at that point, we can do peer-to-peer transfer, right? Transferring the data directly from the network to the memory of the GPU, to the HBM, bypassing the main CPU memory, right? That's another optimization we can consider, again, without any reliance on the GPU direct storage, which is a proprietary framework, right? And this way we can do it on Intel GPU, on Slingshot, or probably on any type of GPU network, right? That would be the beauty of the approach. So there are two modules, PyTorch module. First of all, there is the data loader module, actually implement the dataset abstraction of PyTorch for you who are familiar with it. And there are effectively two types of dataset that PyTorch support for loading. They are the iterable dataset and the map style dataset. The map style dataset, you just you need to access the entries by an index, right? So you have this notion of length, how many index you have in there, get item, and get items with a S when you want to get multiple of them. It does require to scan the tree of the input data set that you want to use, right? To know what are all the entries and to assign an index to them and so on. We've done first an optimization for map style dataset where we can scan the tree in parallel, right? There is a limitation we have found with many of those AI frameworks that at the beginning when they use map style dataset, every single PyTorch instance scan the tree to find out what are all the elements in there, right? And this is very inefficient. So what we did is that we did a parallel scanning inside the PyTorch data loader because DFS has this capability to have an anchor when you can iterate over a dataset in parallel, right? You can split it into different region and scans in parallel the region. So we use multiple thread to scan the region, and you can see here we have done some comparison. The regular scan of PyTorch when it is using diffuse scanning for one process to scan 1.1 million files, it takes 291 seconds, right? With our optimized data loader, by doing the parallel scanning, we took it down to 32 seconds, right? So there is a significant startup improvement. It is done only once when the process starts, when the overall job starts, but still, if you have pretty big data set and a lot of entries in there, that can save you a lot of time. So this is for the map style dataset that are supported and implemented inside this data loader. And there are also the second type of dataset that you can look up are the iterable dataset. They are the one when you can just go next, and iterate over it. So we need to iterate over a number of samples, and we support this one as well, right? PyTorch also has this notion of, for the data loader, of multi-processing, right? So it creates multiple Python threads. And then the data loader has to implement some specific routing that are called worker init, right? That allow us to set up in multi-process environment. It's kind of halfway between multi-thread and multi-processes, right? And they do a bit of both. And we did some optimization to support that and also to share all the pool handle and to be performant across multiple processes. There are a few examples here. If you want to use it into your notebook, you basically usually use the dataset. So you need to, from PyTorch, import dataset, right? PyDAOS.torch import dataset. And actually, you need to replace you use the data loader still that is provided, but instead of providing the dataset that is provided by PyTorch, you use the PyTorch, the PyDAOS.torch dataset that is initialized here, right? Pool, container, and then the path to the subdirectory you want to use it, and then pass it to this data, to the default data loader, and will effectively use our own data loader at that point with our own format, the dataset, directly linked with DFS. There was a result presented at the DAOS user group at SC last year. Google did more performance result, and I'm going to try to replicate this on Aurora, trying to collect result there. But this is some of the result they got on a small test bed. So with one process, a batch size of 32. So this was using DLIO, if I remember correctly, and doing 100K 4 megabyte sample. So here on the left side, you have the bandwidth they got, and on the right side here, the time to complete, right? You can see in the light green, you have fuse, so it takes more time with one process, right? Like 3,000 seconds compared to our own data loader in dark green here, right? And the same thing for the bandwidth was significantly higher. And we also did a similar benchmark with 1 million 5K file, right? And a batch size of 32 with a bit more processes. And you can see here, accelerator utilization was always good, but you can see as you scale the number of processes, the PyTorch data loader was more efficient, right? Increasing the utilization and also increasing the aggregated bandwidth from the node. So there is some real benefit to have it. Again, it's not something to do on day one. You can use Fuse, intersection library, everything will work and you will get good performance, but more of the advanced use case to go beyond standard usage. We also provide a checkpoint module that is integrated with PyTorch. So basically, it overrides the torch.save and torch.load, right? And we checkpoint directly to a DAOS container. So it can be the same container as you use for data loading or a different one. You can configure it as you like. And basically, we provide this PyDAOS, the torch checkpoint class, which manages the connection and provide all the function, basically the reader and writer method to be able to store the checkpoint, right? On the right side here, we have an example on how to use it with DLIO. So you can just copy that if you ever wanted to use with DLIO, and it works out of the box with this way with our checkpoint module. But in practice, the way it works in your notebook is you use from PyDAOS.torch, you import the checkpoint, then you create a checkpoint class, passing again the pool, the container, and if you want to store in a subdirectory, similarly to the data loader before, and you get this checkpoint object, right? Then you can just write the module and load the module, right? Through torch.save and torch.load. That would be the more traditional way to use it in your application. I don't think we have any performance result with the checkpoint module, unfortunately, but I will try to collect the sum and to share.